as we go along. This would be one another example of a hyperparameter. So how do you actually refine your weight? Is it after every iteration, after every epoch, or a subset of the epoch? Yep, that's basically what the topic would be. Students, anything you want to ask me about the module itself, or anything, any other related aspect to the module? Anything you want to ask me before we get started? You would have received the schedule from Dr. Gokul about the test. So that's on 25th of October, Saturday. We discussed actually it's not easy for us to schedule that on a weekday for reasons that you yourself would not maybe be all available for that, depending on your work commitments. It's best for us to put it on a Saturday. I understand maybe one or two students may not be available because of other exams, but we discussed if there was instances like that, then you have to spend a special request to us and let us know. We can then arrange another test for you if required, but it has to be backed by just proper reasons. Yeah, why you're not able to attend the test on 25th of October, maybe for work commitments or for other reason. Maybe you're traveling. I don't know. So there should be some compelling reason why you can't take a test, but I hope it is fine for most of you. Yep. It has been quite difficult for us to find a common ground where everybody's free. When we try to change the date, then someone else is taken up. We've seen that it is pretty difficult to do that. So let's organize it on 25th October itself on a Saturday. I think as per the email from Dr. Gokul, just to confirm, students, as per the email from Dr. Gokul, is going to be from 9 o'clock till 10:15. Yep, and they need to be confirmed. So that's already communicated to you. So the test would be, I discussed with Dr. Gokul again today. His part, so between two parts basically for 1 hour, 15 minutes, so two parts. He also plans to have two questions. And I also said to you two questions, and he doesn't have any multiple choice question. Yep, so all questions will be structured questions, similar to what I will be showing you later today in the tutorial classes. So the question will be of this format. Yep. As per your MSS, it is going to be of 40%, so 20% on marks from my part and 20% on his part. The remaining 60% is on the two assignments. Yeah? One you're working already from me, and one you'll be submitting for the Gokul as well. So that's basically your 100% work for this module. And as you know, there are no exams as such. Yeah. Okay, students, if no question, I just share my screen and we get started. So I would want to first start with logistic regression. So that's an extension, if you want, of not an extension really, but another class of problems where you can use a regression type problem. But here we're not discussing about a variable which can be discrete, yeah, or classification type problem. We're going to look more at discrete type variables, yeah, because linear regression was for an output where it can be continuous, like we saw. The example we took in class was the price of house. Yeah, that's a continuous variable because it can be anything. And there are a lot of other examples which you can come across. But also at the same time, there are so many problems out there which are discrete in value. Yeah, for example, yes, no problems, accept, reject. But there are other type of discrete value problems which is not just binary. It can be other values as well. This can also be extended when it comes to classification type problems. It doesn't mean to have only two classes. I've discussed that before. But in the context of what we are discussing now, we're going to consider yes, no, like we've been doing, but there's no reason why I can't extend the framework to capture more number of discrete states. That's what logistic regression is. The good thing is whatever I'm going to discuss today has mostly been covered by you. It's just a question of picking up the different skills and then framing a new type of problem. So you will see many things, what I'm going to discuss shortly, you already are aware of it. That's the beauty of how we have progressed. Yep, the deadline, sorry, I have changed. It's not 11th of October. No, I've already changed it. Like I discussed, student, it's not 11th October. That was just an assignment I created at the very start. Now it has been changed to 31st of October. So my assignment would be 31st of October. And for Dr. Gokul, 25th of October. Now, is that okay? Yeah, okay, thank you. Yep. So I changed the assignment. I know I got a couple of emails. I think you've been receiving alerts maybe in your email inbox because of the deadline that was set earlier. But that was set at the very start, just tentatively. But over time, we have been able to. Okay, so his submission, I think initially was 25th, but fine. Yeah, but he has set it to 27th. For me, I've set it for 31st, just a Friday. So you would have to submit 2 assignments basically on a Monday 27th and for me on 31st, which is Friday. Yeah. Okay, like I said, I've created and I fixed for Dr. Gokul. I've already created the Google Classroom where you can upload your report in PDF format and also the PowerPoint slide, 5 slides, up to 5 slides. And I will also share with you a Turnitin assignment, a Turnitin class for you to join in as student and to do similarity check. That's important also that we check for plagiarism and make sure when you're writing your report, even if you are doing a literature review, you are consulting other work, make sure you write it in your own words, and anything which you're taking from other people's work in terms of literature review, you reference it properly. That's the standard for academic writing. And down the line, of course, when you will be presenting the conceptualization of a case study, it's very important that that is your own work. Of course, you are inspiring for other people's work to be able to see what could be done in that specific area, but it should be based on what other people are saying in terms of good practices, what are the suitable machine learning models that will be suitable for what you're doing. So this is what I'll be assessing you on. Of course, your report will be there for me to look at what you're saying, but you need to have an appreciation of the literature review, what machine learning technique you're proposing, and be able to justify that. This is why we mentioned about the comparative analysis you have to perform for different machine learning tools. And now you can ask me a question, sir, we have not yet done we have not implemented anything. How do I justify it? It's from literature review. So at this point in time, at the very start of your AI course here, we are sort of, through my assignment, we're training you how do we learn from other people's work to be able to conceptualize. You have to be able to design the AI solution you want to do. Of course, down the line, when you implement it, and then you find, yes, there's scope for improving it, fine. You would, of course, need that iteration, that prototyping, as we say, to be able to implement, test, refine. That's fine. But in this assignment, we are looking for your ability to look what people are doing and to have a good start. This is the direction I would want to take in the case study I'm proposing. This is what I'm assessing you on. Of course, you won't be able to tell me whether it will work or not, but you're able to justify your decision based on literature. That's the first thing. And also, as part of your assignment, what is your expected output which you want to get, and how this will help you in improving a certain process in your company, or be able to maybe bring forward some new features in your company. That's basically the scope of this assignment. Discuss it a couple of times. So I hope it's progressing well at your level. Yes, this is what we'll be doing here to have a few practice questions for this. This is what I'll be discussing, Mr. Ahir. So I'll be discussing the second part of today's session. The tutorial I've sent to you is hands-on practices on questions similar to what you're expected to get in the test. That's what I'll be doing today. I won't be doing all the questions. I want to give certain practice to you. We're going to work on that together, but also give some questions that are left so that you are able to do that work on your own. Unfortunately, I was discussing earlier today with certain colleague. I won't say it is your case here, but we are facing the problems undergrad students where we are in class and discussing solutions, and the students fall in that comfort where they are just taking, I won't say taking note and copying, no, that's not the case, but the fact that they are sort of, I would say, following what you're doing, they think they know what they're doing, but that critical thinking is lacking. When we give them a new problem, then they don't know where to start. So this is what we are increasingly doing, and actually my approach has always been like this. I never solve any tutorial question for students. I never give model answers because this is just pointless, I think. As engineers, I myself have been working in the private sector. You never get a problem which is similar to what has been already documented. So you need to have critical thinking. That's the beauty of being a professional. So we always guide you, but then we want you to think aloud. I do lots of programming classes also for mechanical engineers, and you know the ChatGPT around there, they can just write the program statement and they get the code. But how about the thinking behind the code? How about starting from scratch and thinking, how do I go about just writing a few pieces of code and to implement the problem? So that critical thinking is very important. I think that's a very key skill you need to develop, especially for UMSC students. So just to summarize, so I'll be doing, of course, a session now in the second part on the tutorial worksheet number 2, which I've circulated already. But before we do that, students, I would want to cover, I hope I answered your question here. Yep. So let's get started now. I'm just going to share my screen and we cover the logistic regression I was saying earlier. And then we're going to go to that worksheet on linear regression. We covered that last time. So I will just do a summary of it and then show you another approach called stochastic processing, which is another term you can come across. When you are, no problem, students. I'm very happy when you interact and ask questions. There's nothing to be able to. Yeah, go ahead.
Thank you.
Yeah.
No, that's it. That's my question actually. I just wanted to know for the assignment, how will we go about for the expected results?
Yeah.
Should we actually assume that this is based on our findings? We think that this model will do fine, and this is the expected results of the findings that we had, or we are supposed to implement something at least to have an idea?
No, you're not expected to implement anything. So what I said right from the start, because this is a module on AI principles. So AI principles is really equipping you with methods and techniques for you to be able to go ahead. I understand you have other modules on AI application, machine learning application. There maybe you have some preliminary coding to do and some data set you have to implement. But let me explain to you in more detail. Good question, Ahir. A very important key part of the assignment is that literature review. This is what's very important to choose well what papers you are referencing. It's not just a descriptive analysis of what people have done. It is very in-depth. You don't need to cover too many papers as well, but things which are very relevant to your work. When you start your assignment, it's very important for anything you're working on, you always have a problem definition. Yep, this is what I have identified as a problem area which I'm trying to solve using AI. That's very important for you to define that well. And then you are learning now from literature what tools people have tested in that area, different variations, and people would have commented, especially comparative studies, because you ultimately have to do that. What tools you have tested, what sort of architecture you have used for models, what sort of, if ever you are covering machine learning in terms of deep learning or neural network, what sort of network architectures you have used, because you're not testing anything, you will have to propose that particular solution. Then it's important, then you would adapt it to your case study, to your specific application based on the factors that people have used in literature. You can say, yes, I will use these factors, but at the same time, you have the opportunity to say, yes, based on my knowledge, based on feedback from maybe your peers, I would also want to consider this and this factor. Doesn't mean you have just to replicate what people have done. And you will see in the more recent context, there might be some nuances, some differences in the process you want to implement. But based on what people have done, you can say, yes, this is generally what literature recommends, but I would want to do this because for this and this reason. That's one possibility for you to bring your own professionalism in your assignment. Now, what about the anticipated result? It's pretty straightforward. You have a problem area you want to solve, and you have reported findings in literature, what sort of accuracy people have got, what sort of results they've got. So how does that map in your particular situation? What you expect to get when these results you have got in literature is transposed to your case study? And in the context of your own work, how this is expected to improve your processes. And again, that's not generic, because you're working in a very specific context of your work. Is it possible for me to say, yes, based on this proposed solution, this is what I expect to happen in my workplace or in the organization I'm working in terms of a results reported in literature? This is what I'm saying. So anticipated improvements, anticipated benefits, not just qualitative, but as far as possible based on reported results in terms of accuracy, recognition rate, or maybe even in literature, if people have commented for a specific context, which is similar to your context, what were the benefits? So does that transpose in the same way to your case, or is there any changes which you expect on that? So again, there is I would say, heavy dose of literature review, yes, but you also have opportunity to comment how this applies to your context and how this will be same or different in your context. I hope I answered your question, Ahir.
Yes, you did. Thank you.
Thank you. Okay. Okay, students, any further? Yeah, go Ismail. Go ahead.
Before you start on today's session, would you mind doing a small recap on the previous gradient descent session?
Yeah.
Like what you have the points, and And then how do we use the gradient descent? I don't understand this clearly.
Okay, fine. No problem, Ismail, because I wanted to actually present the one extension of that called stochastic, but I can go back to the batch one. That's no problem. So I will do an overview here. That's not a problem. Yeah, I will do that. Like I said, this is for the linear regression problem. I not expected for the tests that you will get to do hands-on calculation now, because I need to pick and choose what would be covered in the 5 weeks I'm with you. I can't just overload you with so much content. But the purpose of a worksheet for you was to have a very strong foundation of what the gradient descent is and how it works. But you won't be asked to actually implement it and do calculations by hand. Hand calculations would be for decision tree learning, for perceptron learning, and for multi-layer perceptron learning using backpropagation, because this is what is in your tutorial sheet, which we will cover later. But for the gradient descent, you have the worksheet there for you to see and to play around to understand how come when I go in the direction of a negative gradient, it is optimizing my loss function. Yep. So of course I've put a mix and match of exercises in this module so that you have a good grasp of AI principles. We can't present all principles to you, but hopefully through understanding of these fundamental ones, when you're going to learn other things, it won't be that difficult. Again, today I'm going to present logistic regression, but like I said earlier, most of the things that you would need to know to be able to understand logistic regression have been presented to you already. It's a question of assembling the skills. This is what I want you to get from this module here. There are bits and pieces we are presenting to you, but as you start learning more later, this would be a very strong foundation for you to have a very good grasp of AI. Yep, this is what we are going ahead. So let's start with that itself then. I'm just going to do a recap of the linear regression. Yep. And in the sheet that we have, you also have all the equations. Is there any problem on the equation first? Yeah. Is there any problem to understand the equations? Anyone? Do you want me to go deep into the equations or the equations that were presented? So I'm referring to these equations here. This one, not really. I can go back on this one later, but these equations I'm referring to. Yep. So this equation here, not the delta W, but this fundamental loss function. Yep. So loss function here is based on mean square error. Yep. So you are finding the mean square error between your the model prediction and what you're getting from your data. Yeah, basically this one would be predicted from your model parameters, while the y dash here is basically what you have here, and then the yi comes from your training set. This is what you want to get. So you would see here this term, what you find 1 over m summation I is equal to 1 to mf. This term there is basically the same here. Yeah, because the loss function is the same for your process you are trying to solve. What differs between these two is simply, in this case, I'm trying to find the derivative with respect to weight because I'm trying to adjust the weight. Yep. And in this case, I'm doing a derivative with respect to bias because I'm trying to adjust the bias. That's the only difference. Now, what I did last time, I explained to you why from here we are able to come here. Yeah, basically, this is the formulation of the derivative. Any question? Yeah, go ahead, Ismail. Yeah.
Yes, it was about the spot itself. So
yeah,
I'm trying to picture it. I have a line I have my coordinator plotted a line.
Yeah.
Okay. So now the loss function, what is going to do? It's going to change the gradient of the line.
Yes. Let me just go back to this spot there. Just to answer your question, Ismail. I think it's important for you to get a good grasp of that. Let me just go back to lecture 4. Okay. So I hope you can see my screen, students. So I'm just going to go to one specific slide, which is going to answer the question here. Yeah, this one here. Can you see that blue line here? That blue line is the equation you get from the model. Yeah, and this line there in 1 dimension is going to look like this, but in 2 dimensions start becoming a plane. And if you go to high dimension, I can't picture it, but you can start thinking how it's going to be. So if you have two inputs in your process, let's say it is x1, x2. So you have w1, x1 plus wx2. Then, of course, it becomes a plane. Yep. But just for the sake of explaining what we're doing, we just consider one variable to start off. Yep. One variable is x1. So if you have an equation like this, where you always have, just like we covered for perceptron, for every input, I need to have a weight, and the bias is there always on that specific model. So this one is quite, I would say, analogous to what we did for a neuron. But we are not dealing with a neuron here. It's a mathematical linear regression problem. Now, as you play around with W and B, it's clear that you are shifting this model here, the gradient of it, which is the W1, and you're also shifting the intercept B. So currently, you can see a line there, but it may not be the optimum line. The optimum line will be when you are, so if we go there, when you are minimizing all these distances. This is what the optimum B and W would be. Is it clear now what I'm saying, Ismail? So this blue line you find there is not fixed. You start somewhere, and then you measure your distances, and then you start refining all this. Now, how do you refine? This answers the question. When you're considering many B and W, of course, the B is a bias, and the W, for this situation, is only one input. This is why I can plot the loss function. But if I start having x1, x2, x3, x4, I can't plot the loss function because it is multidimensional. But the approach to move from one point to be able to come to that minimum is the same. It's based on gradient descent. Now, what is gradient descent? If you want to understand it, it's very simple. If I release a ball somewhere, the ball by gravity will always move in the direction of a negative of a gradient. Yeah, and this is basically what gradient descent does. So if I want to adjust the weight, I will find on this loss function convex shape, what is the derivative of this loss function with respect to W? Yeah, if you want to adjust W. If you want to adjust B, then I'm going to find another derivative, which is respect to B now, and I will use this derivative to adjust my bias. In this case, you find only one W, just to explain. But let's say you have a problem where you have two inputs. You have W1, W2, which I can't depict, unfortunately, because you're already into 3 dimensions. We can't depict here. Yeah, but same approach. If I want to adjust W1, I'm going to find a derivative with respect to W1 on that loss function surface. And similarly, I will find another derivative, delta W2, to be able to again adjust W2. If you have hundreds of inputs, I will have to find hundreds of derivatives. Yeah. So this is, in this context, I'm explaining for one input, but there's no reason why I can't extend that to any number of inputs using the same method. So what you find here, students, this one here is a general expression how you find the derivative for one input. But you can extend that to W1, W2, W3. What happens if I have W1, this X becomes X1. If I have W2, so X becomes X2, W3, X becomes X2. That's the only change that happens. So it means from this loss function you find there. Now, when I was explaining loss function before, what is a loss function? A loss function basically gives me an indication how good my model is currently. This is what a loss function is. So it gives you an evaluation where I am currently in terms of my parameter B and W, how good is my fit? And how do I get that fit? By taking the difference of what the model is giving me and the difference with what I want and squaring it. Now, why square? Because I don't want to see the sign here. It's just a distance measure. So you need a loss function to understand where you are currently in terms of B and W. How good is that fit? And how do I assess that? By taking the difference of my model and my target, which is in my data set, I square it. And in this case, we're using the mean square error. So I also divide by the value of M, which is the number of inputs in this case. Okay. Now, from the loss function, what we saw earlier, the loss function would look like this. And I want to find the derivative of a loss function with respect to a given parameter. So I can decide where do I move. And this explains it well here. So again, that's very simplistic, just one. So this graph is showing here only one value I want to optimize. And this is a loss value. And what you can see here, I need to move in the direction of a negative gradient. If I'm here, I need to find the gradient here and move in this direction by small amount decided by alpha, the learning rate. If you are on this side, you're going to again move in direction of negative gradient. If you do that consistently, step by step, you are expected to move to the minimum point. So to be able to find that, there are two important elements you have to be able to optimize your problem. First thing, you need to have a loss function. The loss function tells you how good you are at that point in time. If I know how good I am, I need to have an algorithm to make me move to a better place. That algorithm is a gradient descent. The gradient descent tells me, yes, I'm here currently. How do I move to a place where my error is being minimized? And how do I do that? Here. I'm somewhere here. I start moving down. I do that step by step. Yes, go ahead. Any question, further questions? Fine, go ahead.
And how does this... This is what is called a local or global minima. So how does this relate to the line or the gradient over there?
Which line? Yeah, okay. Let me just show you the line. So maybe the confusion here is when if you look at the diagram here, all the values of W and B that you are seeing correspond to a line that you are actually applying. So the blue line you saw earlier, this one, you have an unlimited number of blue lines. This is a model. So all this grid you find there between B and W are a range of lines or model lines. Now your task is to find which is the one I would choose, and it is found at the very bottom here, because this is minimizing my loss function. Now what to talk about global and local minima is very important concept. In this case, you have only one minimum because I'm dealing with only one W and one B. What you're talking of local and global minimum is quite a mathematical optimization problem. This surface there is convex, but you may have lots of local minimum and you don't want to get stuck in them. Yep. And how you decide what is the local or global minimum? This is a learning rate. If you go too slowly, then you can get stuck in a local minimum. You don't want to move. So imagine in this surface there, you have an overall minimum here, but let's say you have a smaller minimum here or here and there. If you move too slowly, you can get stuck in that local minimum. And this is taken care of by other mathematical methods. Yeah, like the learning rate is one of them. And sometimes they input a term called a momentum term. What does a momentum term does? Of course, we're not going into all this because like I see, it's a mathematical optimization technique that you're talking here. How do you prevent the optimization algorithm not to be stuck in local minimum? One approach taken is called a momentum term. Imagine you have a ball here. Yeah, your ball is rolling and you have certain local minimum. If your ball has enough momentum, it will not get stuck in the local minimum. It will just go over it and then still go and settle down in the global minimum. And the global minimum is what you want to be at. Imagine this surface was not as perfect as you're seeing, but you have certain local minimum somewhere. And if you get stuck here, you will get a value of B and W. And this would not be the optimum blue line here, which is minimizing your distance to your points. What you find there as the peak points are your data points in your training set. Yep. And the blue line there is you start somewhere with a value of B and W. Yep. And then based on the distance you get, and you calculate a mean square error for the loss function, you are able to see this is where I am and this is where I can start moving away. And for every step you take, you get a new value of B and W, you get a new blue line. The blue line is not fixed, it's just changing every time. And ultimately, you want to reach a point where you are minimizing this distance between your point and your model. Is it okay, Ismail? Is there any further question on that?
Yeah, I mean, not clear completely, but I mean, you can go ahead. I'll need to.
What is not clear, Ismail? I think it's very important that you understand the blue line there has an equation, very simple, B plus W X. Yeah, if that is X, then that is Y.
The blue line, the linear regression, and I've understood the curve, like going to the local or global minima.
Yeah.
What I'm not seeing is the connection between the blue line, like when we are doing the graded descent, how is it impacting the line here? This is what I'm not.
Let me explain that again. Let me explain that. It's important you communicate these things to me, and you should be able to see that. Look at this equation here. So when you ask question, I can help you with that. Yep. So once we understood that, we want to use a method called gradient descent. And basically, what it is mathematically telling us, we need to move in the direction of a negative gradient to be able to go to a minimum point. Of course, we want to go to the global minimum. Like Ismail mentioned, you may have local minimum, but you need to use some techniques to do with the learning rate or the momentum terms. This is, again, things people have tested in literature. We will not be going along this line. It's I would say, pretty mathematical field, but you can read a bit on that. Yeah? You want not to get stuck in local minimum, like Ismail said. Okay, now, once you move in this direction using that equation, so we understand here from the loss function, we are able to find a gradient. This is what the value we got for the weights. Now, this equation answers your doubt, Ismail. Yep. So currently I have a given weight and a given bias, and this leads to a given line. How do I move from this line to the next point? I'm using the weight slope value. This was derived from a loss function. And the learning rate, we know what it does. It controls the speed of your training. So using this equation, this simple equation here, I'm able to refine my weight, and similarly, I can refine my bias. When I'm refining these two, my blue line is changing. My blue line is starting to move in a direction, moving in a direction where these distances you find there overall will be minimized. This is what basically is happening. You want your overall task is to minimize the distance between your data point and the model you're creating. Initially, when you assign random values, it will not be minimum unless you have you're very lucky. Yep. So initially, it will not be minimum because they randomly initialize values of the bias and the weight. But then by moving with a new weight is equal to all weight and new bias go to new bias go to all bias minus the gradient multiplied by the learning rate, you expect that this line will start shifting up and down ultimately so that this distance is minimized. But what is a relationship between the tuning you're doing for the loss function and the gradient descent and how this is impacting your model? Right? Pretty simple, but again, students, this is on one dimension, but this occurs for any number of dimensions. You may have a number of features you may have in your data set. Even if you have 15 inputs or 25 inputs, the same process is applied. Although we can't depict it because it is in dimensions more than 3. Unfortunately, we are limited to 3 dimensions. We know that. Yeah. But the same process happens. You are going to optimize your weight for every input iteratively, step by step, so that ultimately the distance between your data point, even if it is in 100 dimensions, and a hyperplane would be minimized. This is how you can think of it. Okay, students, I will just now maybe just relate to what we did last time. So I've renamed this sheet there _batch. Yep. And this is what I've just explained to you, so it fits well. You have this equation here for tuning the weight. So to be able to tune the weight, remember you have the new weight is equal to the old weight minus the gradient times the learning rate. Where do we get that slope for the weight is from here. So by differentiating this one here, we use chain rule. We saw that you are able to get this equation. And similarly, if you want now to adjust your bias, you would use the same loss function here, but differentiating your bias, your loss function with respect to your bias, you get this term there. And as we observe, the derivative with respect to bias has no x in it. Yeah, we explained also this on last Saturday. Now, what we implemented next, student, in this specific case there, we started with value of b and w. We keep it fixed throughout the epoch. So this is one epoch here. And to implement this, this one here to get the slope, so as you can see, we need to find the difference between your model and the value. So first thing we start doing is we find the value from the model. How we do that is simply equal to b plus w times x. Yep, the model for one input in this case is b. So the b is here plus w. W is that column there times x. So this is for that particular data point. We do the same thing for all the different data points. So you are able to get your target value, this one here. Yep, the y you want to get, and you also you get the model value. From these two, you are able to calculate this value here. Y dash is simply this here, what you get from the model, and then subtract. So we are implementing this equation here. Subtract what you get from your data set, and then multiply by 2x. And x, of course, in this case is area. If in our problem, which we are trying to formulate, there were 2 inputs. There was area, and let's say you had something else. Let me think of something. Maybe proximity to services, something like this. Yeah, let's say proximity to services or proximity to a bus stop. 3 meters. Yeah, let's say this is the factor you would choose. Let's say you had this proximity in meter. Yep. Then you would have a second input. Then you would need to work out y prime minus y times 2x1, where x1 is your area, and y prime minus y times 2x2, where x2 would be the distance to the closest bus stop. Then you will need to work out 2 slope value, one with respect to the area and one with respect to the proximity of the bus stop. Yeah. So similarly, you can extend the sheet to have more number of inputs. There's no problem. Yeah. But coming back to a problem here, students, we have only one input. So you work out this factor here, this y prime minus y times 2x. So we got this one here. Now we need to accumulate that. So we sum all that over one batch. We got this value. And of course, we divide by 11 then, because we have 11 samples in all here in one epoch. So we're able to do that. And how do we refine now your weight? Is simply if you look at what we did here. Let's look at this one here. So we take the current value of your system bias. Sorry, let's look at weight first. Yeah, we take the current value of your weight minus the gradient. So we got this gradient here times the learning rate, which is alpha 2 in our sheet here. So this is simply implementation of the gradient descent. And as you can see, the value of B the values have changed from 3 to 1.07958. Yep. So this is a refinement. So if you had plotted the blue line earlier with these parameters, you would have got a given slope and an intercept. And now it has been changed to another intercept. And how we did that? By defining your loss function, finding the slope, and then refining it using the gradient descent algorithm. So similarly, to find the new bias, you need to now define a slope with respect to the bias. This is the equation to use. Yep. So again, we do that for every data point, and then we find one global value to adapt. Yep. You see why I call this one a batch processing. In a few minutes, I will explain the stochastic one what it is. Batch means I take the whole epoch and I adjust your weight only after having gone through the full epoch. You see what's called batch. So you do only one adjustment per epoch, which is not the only method. You can also adjust for every iteration, which we did in the perceptron case. And you have different methods you can use to adjust your weight. You have pros and cons. So you have the advantage with the batch processing, but you also have disadvantages with that in the sense you require slow, because you're making a change at the end of every epoch. If you change for every single iteration, your learning process can go fast, but unfortunately can become unstable as well. You can get stuck in local minimum because you're making very dynamic changes. Yep. So you have a pros and cons there. The intermediate, if you want, the hybrid will be mini batch. Yep. So you are not using the full epoch. You use only, let's say in this case, you have 11 data points in your data set. You use, for example, 3 only. So you don't use all the 11 in batch. You don't use every single like in stochastic, but you use a mini batch. So these are different variations you can also implement. Okay, students. So once you get this one here, you can simply correct for your bias now. Same equation, same method. You use the current bias minus the slope you've got. This is a slope multiplied by the learning rate. So you get a new bias here. And this is brought down here. And then we use the same method to work out a new predicted value from the model. Again, we work out the mean square error and so on. And we work out again this parameter and we just keep refining. This is what we covered last Saturday, students. And this is based on one approach called batch. Now, what I've implemented for you and I want to present now is called the stochastic approach. Yep. So same equations that you are seeing here. So exactly the same data set, but look at the BNW now. I'm modifying your BNW after every iteration. Yep. So using BNW, I'm estimating my output, B plus WX, same way. Yep. And I'm also able to work out this parameter here, which is this one here. I'm able to work it out. And I get a weight slope value, which is not now for the whole 11 data set divided by 11. No, I take this one itself to be the slope. And I correct the weight immediately. Yep. So new weight here would be simply the current weight minus the gradient times the input. Or times learning rate, sorry. Learning rate. So you get a new value of weight here, which you bring down immediately here. Yep. So this one is called stochastic approach, where you are refining for every iteration, whereas this one was refining for every epoch. So you have these extremes, like I'm saying, but the middle way would be you use a mini batch. So you choose a subset of your data set to allow the training to progress fast enough, but yet be stable. Because when you consider the whole data set, you are more stable here because the change you're making is representative of the whole data set you have. Whereas, but if you do that, unfortunately, the training would go slower because you're making a change on your model parameters, in this case, BNW, only after every epoch. This is called batch processing. Yep. If you take the other extreme now, you make a change every single iteration, your training is expected to go faster, but you can also face problems with instability because you're making too fast changes. So you can then fall into local minimum and you can get issues with convergence. This is a problem. Yep. So like I said, the middle way would be to use a subset of your data set to do the changes. It's called mini batch processing. Yep. Now let's see what we get when we apply the stochastic one. So it's very similar approach to what we did, students. But in this one, we were accumulating all the sum of your values of y minus y dash here. You accumulate the whole thing and then we divide by 11 to have a representation of the of a term here, y minus this one times 2x over 11 to have a representation of a slope over the whole 11 data points. And then you use this representation, this mean value, to make the change on your weight. Whereas here in the stochastic one, you use that value itself to get the weight slope value, you make the change immediately. Yep. So once you get this one, you get the new BNW, you predict your model, you again find this parameter y prime minus y times 2x as per this equation. You adjust immediately your weight here, and you use that in the next situation. Same thing for the bias. And what we see, yes, this one in this case works. So just pay attention to this iteration number you have here, yep, and to the mean square error. So initially your error is quite big, but as you start iterating and you see here, your error becomes small. Yeah, it's just continuously being minimized. And if you plot a graph of the mean square error against the iteration number, you get initially start picking up because this is the first iteration, but then it quickly starts falling and become very close to 0. So you can see here, using a graph of the loss function against your iteration number, you can see as your training is progressing, you can have if you want, a real-time graph showing how the error is evolving. And that will give you an indication that, yes, my process is working fine. It is going towards minimization of the loss function. So in this case, both the batch and the stochastic one are working because it's a pretty simplistic case. But as you start doing training, if you're using these two extremes, you may find, yes, for batch processing, it's taking too much time. Or if you use only stochastic for certain processes, you may find, no, it is not converging. It's not converging because of the making changes on your bias at every iteration. Yep. So it's like too frequent changes. You have these two extremes. Now, which one to choose, students? It depends again on the process. And this is what's very important when you're doing a training of your model. You need to see the graph of the convergence of your loss function with iteration. There's no hard and fast rule here, but if you do batch processing, it would converge, or if you do stochastic processing, it will converge. No, it's not that. It's a bit by try and error. That's one thing. But the best metric would be to look at that graph of how your loss function is changing with iteration. If you see it reducing over time, initially it can pick up because it's still finding the path. It can increase for some time. But then if it keeps increasing and then it's fluctuating and remaining high, then your model may need to be, the method of training may need to be changed, or your model parameters may need to be changed, or in the case of neural network we saw earlier, maybe you need more hidden layers. So you need to look at then at your at the machine learning model itself. Okay, students. So I just wanted to introduce a stochastic one. It's a very important principle that you would use in model training. Do I use all my data set to refine my model at the end, or do I choose every single data point to adjust it? These are two extremes. Okay, so I'm sure when you will be covering other machine learning methods, you will come across these terms: batch processing and stochastic processing. And the midway between the two would be mini batch processing, where you have a subset of it. So I've tried to illustrate that using the linear regression model here. Now, if you look back at the perceptron training we did and the MLP training we did, there it was stochastic because at every iteration we were doing a change on your weight and your bias. So that one was stochastic. So now we are putting the whole picture together. You could also implement, for these ones as well, you could also implement batch and mini batch. Yep. So you would be doing adjustment only of the given number of data samples, but not for every single. So there also you can try and see what difference it does. Okay, students, is that fine? Is that fine what I've just introduced here on stochastic and the batch? But of course, based on the same equations. Yeah, based on the same equation. But the only difference is when do you make the change on your bias and your weight. Okay. Now, I prepared some slides for you now. I will just cover that before we take a break on the logistic regression. Yep. So this one is linear regression, where your output is a continuous variable. Let's look at the logistic regression now. Yep, it's a new lecture series. Of course, I will share that with you down the line. And in this lecture series, we're going to cover logical programming also, although I'm not included the slides yet in this slide there. I would add it down the line. Today, we are focusing on logistic regression. By the way, students, we'll be having one more lecture session with you on next Monday. This is where I'll be wrapping up logical programming. Yep, and few other things that is there in your module outline. I'll be wrapping this up. And then in terms of tutorial session, we will have one this Saturday. And then the next one we want to have, like I said to you, we need to plan if we can meet on campus to prepare you well for your through a test, and also maybe discussing your assignment. If you have any question, we can discuss better when we meet in person. So this we plan in due course. Okay, so let's just spend some time on this one here. Yeah. Okay, so again, referring to what we have done earlier on the linear regression module or content. Yeah. Just 1 minute, student, just 1 minute. Just 1 minute, student. Just have a okay, students, let's continue. This one is just making an analogy between what we just covered. We saw earlier that when we do linear regression, your output will be a continuous variable. And some examples will be price of house, which we look at, value of stock, or any other parameter which you have, which is continuous. Yeah, it's not discrete valued. Now, what about variables which provide discrete outcomes? Like if you have questions, will it rain today, or is this email spam, or you have any other outcome which is not just continuous, it's our discrete values. Like I said, it's not necessarily just yes or no problems. You can also have variables which are discrete outcomes. I gave one example, I think, in the past, where if you want to assess the performance of your staff, if you're a supervisor at work, you would give the outcome, for example, as excellent, very good, satisfactory, moderate, and so on. So these are also discrete valued variables, but it's not just yes or no. It's not just good or bad. Yeah, it is different level. For this one also, you can extend whatever we're discussing here to be able to use logistic regression. Okay, so this third bullet point I think is clear. Even if you're talking here of yes-no problems, I'm sure when you would be looking at the organizational processes that you have at work, there are many yes-no problems. Yeah, there are many yes-no problems which can be nicely automated using machine learning. And this would, of course, reduce lots of bottlenecks in the organization, which will improve lots of efficiency in your processes. Now, when we talk of logistic regression, the scope here is to give a probability that a specific class is to be chosen. Even if it is 0 and 1, yes, no. If you have a certain outcome, yes, no, what is logistic regression going to do? It's going to give a probability which of these two have the most higher likelihood of being chosen. Okay, so what sort of function comes to mind when we talk of an output ranging from 0 to 1? We saw that earlier when we were discussing activation function. We have seen the sigmoid function. Yep. So if I just go a bit forward, students, we're going to see how the sigmoid functions look like. And this is one of the main functions which are used when we talk of logistic regression. We'll see this shortly how it works actually. Yep. We saw that when we were discussing the backpropagation algorithm, when we were discussing that we want to have an activation function which is differentiable. But here we are using it in different contexts. There's no differentiation here, students, don't worry. We are actually using the sigmoid function for logistic regression as one of a potential function. You have other functions you can choose, but the important point here, I want to have a function where the output is between 0 and 1 because I want to assign a probability to the class to be chosen. Yeah, so probability is always between 0 and 1. This is why I need to choose an S function, as we call it, and logistic regression is based on S functions. Yep. And one of them, which is heavily used, is the sigmoid function. Now, it's understood here, for example, you can't use tan hyperbolic like we've seen earlier because there's between -1 and 1. Probability cannot be negative. Yep. So you need to choose an S function. There are others in literature you can come across, but one of the heavily used one is the sigmoid function, and we have used that before. Going one slide back now. Yep. So let's read that together. We know probability can range between 0 and 1. Now, we know why we're talking probability here, because you're going to assign a probability of one of the classes to be selected. Of course, the one with a high probability would be chosen. That's true. So what function comes to mind? I've already explained that to you, the sigmoid function, because it ranges between 0 and 1. An interesting point there, your input can be between -infinity to infinity. So very large values of the domain for your X, but your output is limited between 0 and 1. So that's very, very interesting function. So many problems require probability estimate as output. Logistic regression is an effective way to calculate probabilities, as we've just seen. A logistic regression model produces an output between 0 and 1. So this is basically the probability. There's a family of functions called logistic functions. Not sigmoid is not just the only one. You have a whole range of functions, typically called the S functions. Yep, because it looks like an S, whose output has those characteristics. So typically we call this as logistic functions. Yep, this is what's called logistic regression. Yep, and among them, the sigmoid function is a common one, which we have come across before, and this is how it looks like. And now this equation we have used as well. So 1 over 1 plus exponential minus x is going to be the function we'll be using in logistic regression. Again, students, you can use others. I'm not saying the only one, but okay, students. Yep. So let's continue here. What is interesting here, students, is we're going to use what we learned about the linear regression. We're going to use it now to build up to get a logistic regression model. That's interesting. Now, what you find in front of you here is what we learned earlier about the linear regression. Yeah, you had a B, and then you have W1x1, W2x2, and so on. So this one would be actually used if you are doing linear regression. Now, what we want to see now, how can we start with this model and then be able to transpose that and bring it into the range 0 to 1? Yep, this is what I said earlier, students. Whatever we are learning now is sort of an extension of what you learned earlier. Now, before we move on, it's clear here, the parameter B and W, we have already seen how to adapt them already. Yeah, in the linear regression case, we have seen that, yes, you have a loss function and use gradient descent to be able to tune it. Yep, this we have already established in the past. Let's read that together. So logistic regression model uses a similar linear model as we saw earlier for the linear regression, like I just said, but maps the output of that linear model into a probability range. So we first will calculate a Z, and that Z, of course, is not sufficient because this Z will not be in the range of 0 to 1 for probabilities. So what we do next now, we use this Z here, yep, but we're going to adjust the values of B and W1, like I said, but we're going to feed that Z now into the sigmoid function. So Z can be any value from minus infinity to infinity, as we saw. Now we're going to take that Z and feed it in this sigmoid function, as shown here. Yep. So the Z you find here is basically the value here, which include your B, your W's, and so on. And all this B, W1, W2 is what is to be adjusted during the training phase. But this is the linear regression, but we use that now to actually find the Y prime, which is the model value. The model value has to be a probability between 0 and 1, because that's what would be used to decide which of the two classes would be used. Okay, students, so the Y prime here is calculated by first finding a Z, and Z is as shown here, what you see in there. And when you feed that Z into your sigmoid function, you're mapping that on the range 0, 1. And how do we do that? This is illustrated for using these graphs here. And let's spend some time on that. Let's say you have, again, we take a case of only one input and one bias. So your weight for that input is 2 and the bias is 5. Yep. If you plot this graph y is going to 2x plus 5, you get this line here. Yep, you get this line here. And you can find the intercept here is 5, because when you put x0, you get 5, and then just a straight line. Now, what are we showing here? If you have a point here, which is 5, if you map it on the using the sigmoid function, the 5 comes somewhere here, and you can work it out by replacing the Z here by 5. You get 1 over 1 plus exponential of minus 5. You will get a value close to 1 here. If your Z was, let's say, a value of 0 here, it's going to be mapped onto the value of 0.5 exactly here, because 1 over 1 plus exponential of 0 is 1 plus 1, you get half. So this was 0.5 here. On the other hand, if you were around minus 10, if you replace 1 over 1 plus exponential of minus 10, you're going to get a value close to 0. So what we are illustrating here, based on the value of your B here and your W, you will calculate a Z based on what we learned earlier on linear regression. But you can't stop here. You need now to feed that value into the sigmoid function, which maps your Z onto the range 0 to 1, because we want to have a probability here. Okay, now how do you do training now? Remember, in your training set, it's important that you understand your training set, what will you have? If you have this the input X and your output is Y. Is Y, not Y prime. So very simple data set, just like for the house problem, but your Y in this case would not be continuous. It will be just 0, 1, 0, 1, or yes, no, yes, no. Yeah, it will be binary in this case. So for that particular X there, you have in your data set a targeted value, which will be 0, 1. Yep, 0, 1, this is going to be a probability. Okay, now you are able to get an estimated value for your model based on the value of your B and your W. So as we have said earlier, you need to have two values. The target value come from your training and your model value come from the model parameters. Now, it's not direct here. You will calculate first your Z using your W and your B, and then you're going to feed that in your sigmoid function to get your Y prime. Remember earlier we had taken Y prime minus Y and then we squared it, and then we were able to get a loss function. We're going to follow a similar procedure to do that. Yeah, okay, students, I think we're going to take a small break now, and then because maybe it's a bit difficult to assimilate all that. So it is almost quarter to 6. We resume at 6 o'clock, students, and then we're going to pursue this one. So we spend maybe 5-10 more minutes on this, and then we're going to shift the tutorial sheets. Yeah.
Parce que moi, des groupes haïtiens, il y a un moment, les gens qui sont aquí nous sort, ça va? Pattern 5-7, vous êtes une forme de 5-7. Wait for the sunset, guys. Ça va être là, tout va être en fond. Et puis, venir là, doucement, doucement, maybe. Merci pour le cœur. Un bon salade confit, insulé, aïe, frère, pas côté. Pas côté, mais il n'y a pas côté. Un bon salade confit, pas battement. Pas de moins, qui m'ont la série, les mots sont confit, là-bas. Quand fait la salut, tu l'as dit. Un mot transformé, tu. Et puis, t'as les préparations pour rouler pour finir dans la mer. Allô? Elle est pour venir là, dans la madame. De la scène à de regarde, ça c'est juste une initiative à l'église. Le papa nous a dit comment vous allez moduler ce
Okay, students, let's continue where we left off. So just let's see where our discussion stopped before we just took a brief break. Yep. So what we said earlier was we are still using a linear regression model at the base because you have your inputs x1, x2, and so on. But if you look at your training set in that case, it would look like, let's say you have, let's take a simple case where you have two inputs x1, x2, and you're dealing with a logistic regression type problem. So your output would be, in this particular case, would be a yes, no, or 0, 1, and so on. So it will be binary type of output. And this is what we're trying to assign a 0 and 1 for time being. We are sort of assigning 0, 1 based on the class you're going to choose. If your output is close to 0, means it's a no. If your probability that you're getting at the output is close to 1, then it's going to be the class 1 for the simple binary classification type problem. But like I said, this can be extended to more number of class output. But let's stick to that for the time being. So if you look at your training set in that case, you will have, if you say you have two inputs, it will be x1, x2. And for these two inputs, for every data point, you have a corresponding output, which will be either 0 or 1. That's as simple as that. So if now you start with certain weights, W1, W2, and you have a bias B for two inputs again student, when you plug in, you will get a Z, which is, of course, continuous in that case. It's not limited to just 0 and 1. Now, taking that Z now and feeding that through your sigmoid function in that case, which is a logistic function, is going to now map that Z onto the range 0 to 1. Yep. So the initial parameter tuning would be in this way. So for any W1, W2, and B that you're choosing, yep, it will lead to Z. And the Z, when fed to that function, will map it to 0, 1. So basically, you have x1, x2 in your training set, and you have actually a Y, which you want to target and get. So that will be 0, 1. And you are also getting 0, 1 as a predicted output, which is mapped onto the sigmoid, yeah, as we saw here. So I hope you can see the link between your parameters B, W1, W2, which is going to first create a Z, which is of this form. And then you can map the value you get from that linear model onto your logistic function to get a value between 0 and 1. And that's your output, which you are targeting. And like I've said, this value of Z there can be from minus infinity to infinity, doesn't matter. When you map that onto a logistic function, in that case sigmoid function, is going to restrain your output Y to the range 0 to 1. This is basically what you want. Now, what we saw earlier when we were discussing the linear regression, once you have a Y which you want to get, and you have a Y dash as shown here, which you're getting from the model, you are able now to create a loss function. From the loss function, you're able to apply an optimization process to be able to come to a local minimum, where the local minimum basically minimizes the divergence between your model output and the targeted output. So this step is the same. Now, important difference, however, student, is when we were discussing linear regression, we were using the mean square error to be able to create a loss function. Now, the mean square error, if you read a bit about the reason why we don't choose it for logistic regression, you can read about that. It's to do with range and so on. So for this particular problem, logistic regression, we don't use the mean square error as loss function. We use something called a log loss. I'm going to show you in a few minutes how it looks like, but it is still a loss function. And the method you use to actually use a log function to find the gradient and then from there to shift to new values is similar. So you will still use gradient descent to be able to optimize your model parameters, in this case, a B and W. Yep. But the loss function we use for logistic regression type problem, where your output are discrete, is not the mean square error, because mean square error is well tuned for continuous variables, where your output are continuous. This one you will use mean square error, as we've done before. Now, another important point there, which I'm just highlighting here, students, without going in detail, I hope you would cover that in other modules, but of course you can just pay attention to that and read on that, is the concept of overfitting. So one important aspect you need to guard against when doing training of a machine learning model is overfitting. In a sense, you should not allow your model to train so much on the training data, but when you start applying data which is not seen by the training process, then your model performs poorly. This is called overfitting. Yep. So in order to avoid overfitting, there are a couple of methods we can use, and one of them is mentioned here. It's called regularization. Yep. So we're not going too much in detail of that. Actually, we're not covering that in detail in this module, but you need to be aware when you do training of a machine learning model, yep, you have certain constraints you can put on the training process so that you prevent overfitting to happen. Yep, and some of them are mentioned here. Yep, so one method which can be used is called L2 regularization. That is basically a norm that you're applying there in terms of how your model parameters should behave. You know what's a constraint? Basically, when you optimize a problem, you can apply constraints on how the optimization takes place. So one example of this regularization is called the L2 regularization, and another one is called early stopping. Yep. So I'm not going to detail of these, students, but be aware that these methods exist. Yep. Now, coming back to your the important difference that we saw earlier between your linear regression and the logistic regression is the log loss equation. Now, again, like I was saying earlier, there will be similarity between what you have done before. Now, can you look at this equation here, students? And does that remind you of anything you've done in the past? Yep, what you find in front of you here. Yep, is there any, we are calling this one a log loss function. Yep. Is there anything similar to what we've covered so far, which is which reminds you of what we are seeing here? Remember, yi is your target value and y prime is from the model. Yep. So we're basically taking a minus sign outside, but in actuality, both of these were minuses. If you put the minus inside, you will get both of these terms are minuses. That's one thing. And then the 1 over n is simply an average value. Yep. Do you recall when we were doing the chapter on decision tree learning, we had defined an entropy as minus p log base 2 of p minus q log base of q. Yep. So it is along the same line here. It is actually called a cross entropy. Yep. This one is the cross entropy because you have yi and then you have yi prime. Yep. And then you again have 1 minus yi and then 1 minus yi prime. So we are using something analogous to entropy here. And again, the log loss function is used for logistic type problems. I won't go in detail, like I said at the start of the class. For the linear regression problem, I've gone for the whole step. We took the loss function, we derive the derivative of it. We have shown for a sheet how it takes place, but we will not do it in this case. But whatever principle you've discussed earlier about the gradient descent for the linear regression is also applicable in this case. Once you devise a loss function, now the way you would use that to be able to optimize your model parameters b and w would be quite equivalent to what you have seen in the linear regression case. Yeah, but we won't be doing that in depth because that will be too much. Like I said, students, it's important that whatever you've learned and whatever methods you're learning there would help you to be able to learn new methods because there are so many methods out there. Yeah, even for logistic regression, we've just seen some methods. If you read in literature, there are so many variations of that. Yep. But if ever you're going in depth of that, especially for your project work, you're reading about a specific tool, you should be able to understand what are the differences between them, and whatever you're studying in this module in terms of the fundamental principles of AI will help you to go along this line. But going in depth of everything in one module is not possible. Yep. So how we proceed here, student, actually it's a very last slide. Once you identify the log loss function to be used, then the step is very similar. Yeah, you would need to find a derivative with respect to your bias, a derivative with respect to your weight, and then same method, you would be adapting your weight and the bias step by step based on how we have seen. But for this one, students, we don't have a worksheet because I'm not going to go in depth of every method we are seeing. Okay, now just to maybe do a recap of what were the main highlights of logistic regression. First thing is a discrete value of the output. It's not a continuous output, it's a discrete value. Now, how we are representing that discrete value in the case of logistic regression as a probability between 0 and 1. Yeah, because we are considering here 1 to be one class and the 0 to be another class, like yes, do. We are limiting ourselves to that particular binary classification for now, but it's very possible for you to extend it to multiple classes. It's possible to do that, and you can read on that. How do you extend it to more number of classes? But for the sake of this module, we are considering only binary classification. Now, since your output is just 0, 1, binary, yep, it means that I need to choose a function to map my output to this range, and we chose the logistic type functions, and one of them is a sigmoid function. And how do you actually do that? Based on what we covered before, your model parameters will still be b, and for every input, you will have a respective weight. but same. But then you map the Z onto the probability between 0 and 1 using the sigmoid function. Now, when you're going to do the tuning, of course, you need two things, like we said. You need a loss function. And what we discussed here, the mean square error function we saw earlier is not appropriate for logistic type problems. It's appropriate for continuous output variable, so for linear regression. Yep. When you talk about logistic regression, you need to choose other loss function. And one of the main type is called cross entropy. And this is shown here. And like I said, it's analogous to what we did when we were discussing decision tree learning. Now, once you have a loss function, what we are not going into detail now is once you have a loss function, you can, of course, find the derivative with respect to your bias, to your weight, and then you proceed in a similar way to adapt these parameters to be able to reduce the distance between your targeted value and the model value. Same thing. Yep. But here we are not going into these details. Okay, students, what I wanted to present for logistic regression. I hope you have a notion of what it is and how it is similar, but at the same time different to linear regression. Yep. So if you're given a context of a problem and you are asked to choose a suitable model to be able to represent that particular process, you need to bear in mind what sort of output I'm talking here, how many input factors are involved, and then you can choose a proper model. Now, from what we have just discussed, and if you make a parallelism to what we discussed in MLP, you can also use an MLP to do binary classification. You can also use an MLP to do linear regression. Yep. So neural network can be used to do both. But when you talk to regression, you have linear regression would be used for outputs which are continuous, and you will use logistic regression for outputs which are discrete. Yeah, just as a summary. Okay, students, so this wraps up the logistic regression. We would be shifting now the tutorial. Yep, and then practice some questions together, like I said at the start. Like I just said, we won't have a worksheet for the logistic regression. Yeah, it would be too much for you to cover in only one topic. Okay, students, I open the floor now. If anyone has attempted tutorial sheet number 2 and has any specific problem, any specific doubts they want to clarify before I start just choosing 1 or 2 questions to work together. So is there anything you want to ask me about any specific question in this tutorial sheet number 2? No question at this point, students. So I pick a couple of questions. The first one is theory. Yeah, the first one I discussed already is about the symbolic and sub-symbolic approaches. Just quickly on that, the symbolic approach is the top-down approach. You have similar to what you would use to create a programming a solution to a problem. The sub-symbolic approach is a bottom-up approach. So you have sensing of information first, you create stimuli, and then you build up to information at the top level. So it's a bottom-up approach. And Gardenfors, if you look in the notes, actually said it's not only symbolic or sub-symbolic, it's both of them. But important point is Gardenfors say it is still bottom up. So you do collect stimuli from your process, and then you make sense of it by constructing symbols at high level. That's basically what you need to understand here. In your slides, one example is given on color representation, which we all relate to. So you see color around us. How does our brain actually make sense of color? So we have hue, saturation, intensity, and these things are actually sensed and perceived in our brain as hue, saturation, intensity. By combining the stimuli from these three, you have neural networks in our brain which tunes to that. We are able to make sense of color. Yeah, this is how you can explain by practical example. Now, if you look in literature, you have other examples presented for conceptual the conceptual spaces proposed by Gardenfors, and you can relate to that as well. Now, part B here is in the context of decision tree learning. So the first one is still theoretical. So you should be able to recall the equation for entropy. Yep. So if you talk of decision tree learning, the context we are discussing now is basically again binary classification. So yes, no. So you are able to define a parameter small p, which is a proportion of positive samples, and a small q, which is a proportion of negative samples. And then you're able to define an entropy as minus p log base 2 of p minus q log base 2 of q. Yep. So this is what I've just referred to earlier when we were discussing the log loss function. It is similar to that. Yep. But although not exactly the same, but it is similar to that equation. Now, you would recall when we did decision tree learning, it's not sufficient to use only entropy to find actually any particular branches or node that you want to test. You're going to have to define something called information gain. Yep. So information gain is based on entropy. Now, if you look in your notes, you will see how it is defined. Now let's try students to work on part B here, B second part there. Let's try to do the hands-on calculation here. Yep. So this problem is a generic problem. We are saying you have three input features which are used to classify an output Q. Yep. And the way that the problem is framed here, you are given in a summary form already. It's not in a detailed form where you need to start counting how many A1 values of A were it high and low. So if you are given the raw data, you would need to do that. And refer, of course, to play tennis example, and then you have a table that actually does a summary for you. So for the sake of your test, it will be likely that you will get the data in this format because you don't have enough time to do the counting and then to be able to represent it. How many yes and no do I have a particular state, and you have to do it for all the states. So it's a bit of a lengthy process, although if you have to do it from scratch, this is what the software would do. Yep. But for the test, you would get it in this format. Now, one important observation, students, if you look at this column here, it means for the variable A, I have 15 plus 7. Yep, 15 plus 7 is 22. So for the of course, a common table here, A, B, C is a common training set. And in A here, you have some data points where you have A1, some data points where A2. So you can see here, the input variable A has two states, possible states A1, A2. On the other hand, the input B has three possible states, B1, B2, B3. And the input C has two possible states, is C1, C2. This is what you can see here. Now, in a practical case, for example, A represented weather, or maybe representing wind, yep, then A would be weak and A2 would be strong. So these things, of course, can have very specific values for a given process. Yet it's very generic. It's saying like input variable A has states A1, A2, and so on. Yeah, but of course, this can be transposed to very practical cases, like we've seen for the plate tennis example. Now, if in your data set, the input A has state A1 on 15 combinations, which correspond to yeses in your output, and 7 no's, so already have 22 samples covered here. And in the other ones, which are exclusive in this case, for values of A2, you have 5 yes and 3 no's. So it means you have 22 plus 8, you have 30 data points. Now, this 30 data points should also be relevant for all the ones because in your training set, you have 30 data points. These data points are common for B as well. So if you take B1, you have 7 plus 2. So you have 9 here. So for 9 data points, the input B had values B1. Yep. Similarly, you have 13 and then you have 8. If you take 9 plus 13, here you get 22. 22 plus 8, again 30. So it should be everywhere 30. The number of data points is not 30 plus 30 plus 30. Yeah, because it's a common table here. Now, similarly, if you take the input C, if C1, you had C1 for the state of C on 17 instances, and for C2, it was 30 instances. 17 plus 13 should again be 30. Now, another observation, look at the number of yeses. 15 plus 5 is 20. So in the 30 data set, you have 20 yeses and 10 no's. When you count now the same thing for B, it should be the same because the table is common. 7 plus 10 plus 3 is also 20, as here. And 2 plus 3 plus 5 is also 10, as here. So similarly, if you take for the states of C, 12 plus 8 is 20, which is again 20 yeses. And again, here you have equal number of yes and no's, so again 10. So this is very important. Yep. So the number of samples should be the same for A, B, C because it's a common table. And the number of yes and no should also be the same. And one common mistake by students, when you would want to find the number of samples, don't take 30 plus 30 plus 30. It's actually 30 data points. That's important. Now, how do we proceed next? I'm just going to bring that into Paint. Let's do one example for decision tree learning. I will just get you started, students, so you can go ahead and complete it. Yep. And we'll do one example on perceptron and one on MLP. This is basically the hands-on calculation I'm planning for you for the test. Like I said, you don't have hands-on calculation for linear regression. This is just descriptive for the test that is expected from you. And of course, to be able to do that, I got a question earlier. To be able to do that, you would need to recall the equations. If you need to explain how the decision tree, how the linear regression works and how you use a gradient descent, you would need to code some equations, yeah, for the loss function and for the slope and so on. So it's good if you know these equations. Now, how do you go about, students? How we did it in class? We can start defining the main collection S. The main collection S is for the whole sample, and we just concluded you have 20 pluses and 10 minuses. So as I'm doing that, students, I encourage you to do that in your copybook as well at the same time. So this we concluded here that in the whole collection, the whole table, you have 20 yeses and 10 minuses. You can find that from A, from B, or from C because it's a common data set. It should correspond for all of them. So this is your main collection, and from here, you are able to work out a P, which is equal to 20 over 30. So you can say this two-thirds. So this is the number of proportion of positive samples. And you can also work out a small q, which is 1 minus p, or 10 over 30, you get 1 over 3. So at this point, you have been able to work out a proportion of positive and negative samples. And from there, you can work out the entropy for S, plug in your equation, so minus p multiply log base 2 of p. So for the test, you just make sure you have a calculator which has log at least. If you don't have log base 2, you need to know how to change base. But if you have log base 2, it's easier for you. Yep, log base 2 of q. Yep, so this is the calculation. We just plug the values of 2/3 and 1/3. You are able to get the entropy of your full collection. Yep, so I hope you can do that. So you get an answer here. Yep. Now, next thing, we need to create sub-collections A1, A2, and A3. So we are aiming now to find the gain in using A to classify S. This is what we are trying to work out. Yep, so we want to work out this one. So let's do this one first. To be able to do that, we need to find the entropy for the sub-collections A1, A2. In this case, A has only 2 values, so you have 2 sub-collections. Now, these sub-collections are 15 plus 7 minuses. So 15 plus and 7 minuses. So from here, you are again able to work out the value of P for this case, which is going to be 15 over 22. And the Q in this sub-collection would be 7 over 22. And you are able to work out the entropy for the sub-collection A1. Yep, so again, you plug in these values, you are able to get this one here. Okay, similarly, you need to work out A2. Now, A2 is a collection in square brackets. As you can see, this is the format you have to write it. It's 5 plus and 3 minuses. Okay, so from here, again, you're able to work out. So the 5 plus and 3 minuses come from here. Yep. So you're able to work out your P as 5 over 8 and your Q as 3 over 8. Yep. So once you get that, you are able to work out the entropy for sub-collection A2. Yep. So similarly, just plug in the equation here. You get the values. So far, you've been able to work out the entropy of your whole collection, the entropy of the sub-collections A1, A2. You're now ready to work out the gain in using A to classify S. Yep. So it is equal to entropy of S minus the proportion of A1. Now, how many items you have in A1 is 22 out of 30 multiplied by the entropy of A1. So the answer you get here, you have to bring it down here. Subtract the second value is A2. So A2, how many terms you have is 8. So 8 divided by 30. So proportion of 8 of A2 is 8 over 30 multiplied by entropy of A2. So you would here be able to get the gain in using A to classify S, students. Now, of course, you have values here. Anyone got a value here? Maybe you can share just to share across the class. Do you have a value for the gain in using A to classify S, students? Do you have any value? Just share in the chat if you have. To be able to get that value, you need to have this value here, this value, and this value. Yep. So I'm leaving this open here, so you have an opportunity to work it. But do you have an answer for the gain for A? Anyone? I see message here. I got a question from, sorry, I missed that because we don't get the notation. Yep, from Ranjit. Does the sigmoid function apply only to linear graph? Thank you. The sigmoid function applies only to the linear graph. So you will recall how we are using the sigmoid function here. Just to go back to logistic regression, we were finding a z here from our linear model because we are able to use the value of b and w's to be able to work out the value of z based on the linear model. But we want to map that onto the range 0 to 1, which is a probability range. This is where we use the sigmoid function. I'm not saying it's the only way to do it. The sigmoid function is one of a logistic function you can use. That's one thing. And we are using a linear model here to be able to capture the B and W. There's no reason why you can't use a non-linear model as well. Yep, we are not yet covered nonlinear regression. We will cover that briefly in the last session. Yep, but for time being, we are saying if you want to map the B and W to be able to calculate the response from your model, you can first go for a linear model, and then that could be fed into the sigmoid function. But you can also choose a nonlinear model as well. Okay, thank you, Ranjit. Yeah, we're going to come to nonlinear regression just to tell you what it is. Yeah, we won't go in detail too much of it in the last session next week. Okay, now any value from you students for the gain of using A to classify S? Anyone has a value based on what I've just explained? If anyone has worked it out, else if you don't have it, student, we can work on this. So I hope it is clear what you're doing now, and it's just a question of computing. Now, next step, I've just explained for B now, and then you can wrap up the whole question, do for C also. And ultimately, once you have the gain in classifying S using A, using B, and using C, if the question asks you, let me see what the question is about. The question asks you here, by carrying out suitable calculations, determine which input variable should be used as a root node of a decision tree. Yep. So root node decision tree would be the input which gives a maximum gain. So you have to compare the gain for A, B, and C. The one which has the largest value will be chosen as the root node. Now, also it continues here, also describe how you will proceed to identify the branches of a decision tree. So this one will explain it shortly. Now let's complete first the gain first. Now let's try now to work out the second one. I'll just give you again the main guidelines. If you wanted to find the gain in using B to classify the collection, so this is what you want to find out. Now for B, as you can see, you have 3 possible values. So you have 3 sub-collections to work out. Let's start with B1. So B1 here will be 7 plus and 2 minuses. So now once you have defined it in this way, you can work out your P as being 7 over 9 and your Q for that particular subcollection, of course, to be 2 over 9. Yep. And from here, you can work out your entropy for B1. Plug in the equation here, you get the value. Of course, we know entropy is always between 0 and 1. So when you get the value, do make that quality check. Next, let's work out the sub-collection B2 now. So B2, we can say from the table is 10 plus, sorry, square bracket, 10 plus and 3 minuses. So from there, you can put the value of P as being equal to 10 over 13 and your value of Q as being equal to 3 over 13. Okay, and again, from here, students, you can work out your entropy for sub-collection B2. So that also has a value here, you can get it. Okay, now finally, B3 sub-collection B3 would be 3 pluses and 5 minuses. So it means from here, you can work out your P as 3 over 8 and your Q as 5 over 8. And from here, you can work out your entropy for sub-collection B3. So that would have a given value. And finally, you can work out your gain in using B to classify S. Let me write the equation for you. So it's going to be entropy of S, what you have currently, entropy of S having worked out from here. Yep, using 20 plus 10 minus. So it's the main collection. Subtract now the sum of the weighted entropy for the sub-collection. Yep. So B1 we see has 90 values. So 9 out of 30 multiplied by the entropy of B1. So weighted, the weighted sum, you subtract the weighted sum of the sub-collections. Now, why weighted? Just have to see how many elements you have in sub-collection as a proportion of the total number of elements. For B2, we find out 13 here. So 13 over 30 times entropy of B2. And finally, B3, you have 8 out of 30 multiplied by the entropy of B3. It's understood here, students, that when you add 9 plus 13, 22 plus 8, you have to get the full 30. So you have to cover all the different values. Now you get the value here for the gain in using B to classify your collection S. And similarly, the next step I'm omitting now, student, because you can give it a try. You need to find the gain in classifying S using C. And this, again, you need to define the collection C1, C2, get the respective entropies, work out the gain. Ultimately, you're going to choose the input feature which gives you the maximum gain information. Just compare the values, and then you would recommend, or you would conclude that you would choose either A, B, or C, depending on which one gives you the maximum gain. Okay, students, I hope this is okay. You can give it a try. You can then cover this again if you face any difficulty. I want now to explain this part there. Also describe how you would proceed to identify the branches of a decision tree. So once you get the root node, let's say the root node is B. Let's say the root node is B because the gain that you get from B is a maximum compared to A and C. I'm not saying it's the answer, but just take a hypothesis here. Then when you put B as a root node, the outcome would be B1, B2, and B3. You have 3 branches coming out from the root node B. Now, how do you proceed to identify the other branches and the other nodes? You're going to have 3 sub-collections now, B1, B2, B3. Along these sub-collections, you apply the same method we have seen using the gain. Yep. And now, of course, you will not test B again. You will test only A and C. And again, you will choose the one with the highest gain. You would do this procedure until 2 things happen. Yep, we saw that in the notes. Either you have tested for all the 3 inputs along a given branch, you have to stop because you can't check again for another input along the same branch. That's one thing. Or you reach a stage where all the attributes have the same value. You have all yeses, all no, then you have to stop. In the context of this problem, you're not able to do that. You just need to describe how you proceed. Because you don't have the raw data, you're not able to proceed ahead. You need to have a raw data now to create the 3 branches and then to go along these different branches. So in this case, it's a qualitative explanation that yes, once you do the root node, you will get branches. These branches become sub-collections, and now you will use these sub-collections in the same way using the gain information to identify what would be the next node to check, and you will do that continuously until 2 things happen. One is you have tested for all the input along a given branch. So for inputs, you can't just test any further. And the second condition is you reach a given point where all the attributes are the same value, all yeses and all no's, then this becomes a leaf. Okay, students, so that's okay. If you don't have any question on this one, so I've given you some guidelines here. Make sure you work this on your own. Yep. Let's look at question 2b. Yeah, question 2a is very similar to what you have above. Yeah, this one is fine. So construct a multi-layer perceptron with 3 inputs in the input layer, 1 hidden layer with 4 neurons and 2 output neurons. Hence, describe how the backpropagation algorithm is applied to train such a neural network for a given activation function. So this problem has no hands-on calculation to do, but you should be able to explain the different steps, how you will calculate the output of your neurons in the forward pass, how you get the error at the output layer, how you're able to work out an error gradient, and how you're able to correct for the weights and bias using that error gradient, and then how you will backpropagate the error gradients to get the error gradients in the hidden layer neurons. That's what's expected. So if you, let me just draw what first for you. So you have 3 inputs in the input. So 3 inputs, 1 hidden layer. So 3, 4, 2. You have 3, 4, 2. Yep, this one is done. 3, 4, 2. So I'm just going to draw that using a pencil here. So 3, so 1. So this is input layer 3. Let me just check. So 3 are 4 and then 2 output neurons. So 3, now 4. So you can draw 4 here. 1, 2, 3, 4. And then you have 2 outputs. So this is going to be the architecture of your perceptron, of your MLP. Then you have to make sure all the neurons are connected like this, a fully connected network. Yeah, you have to make sure you're connecting all of them as shown here. So same thing for this second neuron, it has to be connected to all the neurons in the next layer. That's called a fully connected network, and an MLP is a fully connected network. Yeah, you have other networks which are not fully connected, but this one is a fully connected network. So same comment for here. When you go from the hidden layer to the next layer, you have to fully connect all of them. So you have your 3 inputs. You can show them here. So you have 3 inputs. So that's the first input. Then you have a second input here and the third input. And you have 4 inputs in your hidden layer neuron, and then you have 2 outputs here. So this is your output number 1 and output number 2. This is the architecture here. Yep. So you can say this is your input number 1, input number 2, and input number 3. Yep. And this you can call it, if you want, Y1 and Y2. The 2 outputs. Now, normally you number the neurons as follows. You number them sequentially, 1, 2, 3, and then you have 4 here, 5, 6, 7, 8, 9. Yep. And we know on all these neurons, not the input layer neurons, but on the hidden layer neurons, you have a bias here. You can call that one theta 4. And similarly, you have biases on all of these, as well as on the output layer neuron. You have a bias here, theta 8 and theta 9 also down here. So you can show all that. Now, you don't need to label all the neurons, students. You can just label some of them. So this weight here is going to be called W14. So it's between neuron 1 and 4. So similarly, this weight here we call W48 and so on. So you can just number some of the neurons. Now, what you need to explain now how the backpropagation work, you can give some equation for some neurons. For example, you can say how neuron 4 is calculated in terms of its response. So you need to calculate capital X4 first. So we saw that. So it's X1 W14 plus X2 times this weight here, W24, plus X3 times W34. You get your capital X4, subtract theta 4, feed to sigmoid function if you're using the sigmoid function as activation function. And then once you have the output Y4, that's done here. So similarly, you do for Y5, Y6, Y7. Then those outputs are used as input in the next layer. So you need to explain that. And once you're able to calculate the output for neuron 8 and 9, you are able now to work out the errors at this point. So you're able to work out error 8 and error 9. From this one, we know we can work out now delta 8, the error gradient, which we know is equal to Y8 into 1 minus Y8 times E8. This is your error gradient. So similarly, you can work out the delta from the error 9. You can work out the delta 9. And using these two here, you can correct using the equation delta W. In general, is alpha times X times delta. So you are able to correct for this weight, this weight, this weight, this weight, if you know delta 8. Similarly, if you know delta 9, you can correct for this weight, this weight, this weight, and this weight. So you just need to mention this, and you can just code that equation here. You can just mention, you don't need to write equation for all the weights. It's going to be too much, just the main principles. Now, one important principle is also to mention that to be able to calculate delta 4, delta 5, delta 6, delta 7, basically the error gradients for the hidden layer neurons, you would need to backpropagate delta 8 and delta 9 through these weights. So for example, if you want to work out delta 4 for the neuron 4 in the hidden layer, normally you would take Y4 into 1 minus Y4, and you would want to multiply this by E4, but we don't have E4. So what do we replace E4 by? We backpropagate delta 8 through W48 and delta 9 through W49. So you are going to say here, multiply by, if I put it on the next line, is going to be delta 8, the error gradient for neuron 8, multiplied by the weight between the two, so W48. But since you have two neurons, you need to add also, you need to backpropagate this one as well through this weight here. So plus delta 9 multiplied by W49. So this would give you the error gradient delta 4. And if you know this one, you can correct for this weight, and this weight. And you can also correct for the threshold. Same comment, student, I forgot about that. Once you know delta 8, you can correct for W48, W58, W68, W78, but also for the threshold theta. And we know for threshold theta, X becomes -1. This is what we explain. So this is all. This is, of course, not straightforward, student. You need to draw the architecture. I need to explain the steps there. Basically, you have to say, we have to randomly assign values for all weights and threshold before we start the training process. You need to also be able next to activate the neurons in the hidden layer first. So you're able to get output Y4, Y5, Y6, Y7. Using that now, you feed forward to get the output of neurons 8 and 9. So you have reached your output layer neuron. At this point, you're able to work out your errors in this output layer neurons. From the error, you're able to work out your error gradient. From the error gradient, you can do two things. You can adjust the weights and threshold connected to these output layer neurons. That's one thing. Second thing, you can backpropagate these error gradients to estimate the error gradient for neurons in the hidden layer. And once you have that, you can also adjust the weights and threshold connected to the respective neurons. This is what you need to say. Once you have completed this step there, of course, you have updated weights and thresholds. Now you're ready to go for the next iteration in the next data point. Okay, students, I hope it is clear, but let's try to do one example where we have to do hands-on for a MLP. And then next class we can do one for perceptron, because perceptron is very simple. Yep, this one is okay. This one is also descriptive here. This one is a decision tree learning. Is it the same values? No, I think it's different. You have a D here and then you have different values. So if this is a good exercise for you, you should be able to do that. Let's try to do question 6. Based on what I just discussed here, we would want to just apply now some calculations. Okay, this one, let's just bring that into a Paint. And then we try to apply whatever we just learned here using this question number 6B here. Yeah, okay, students, let's just spend some time on this. Again, just to tell you what are the main principles you need to know, and then you can do it afterwards. So a multiple perceptron is to be used to learn an industrial process having 3 inputs and 2 outputs. Yeah, 3 inputs, input 1, 2, 3, and 2 outputs, output 1 and 2. As you can see, your training set is going to include your inputs and your output, but has nothing to do with your hidden layers, as we say. Construct an MLP with a single hidden layer consisting of 2 neurons and carry out 1 iteration using a suitable activation function, learning rate, and values for the various weights and thresholds. So here's an open question. We know we need to assign initial values for weights and thresholds, so we can just take random values here. Yep. And you are also asked to take a suitable learning rate. So you could choose, for example, 0.2, 0.1, should be between 0 and 1 normally. And then a suitable activation function, we learn about sigmoid, so you can use sigmoid. Let's first draw the neural network. We are said it composed of 3 inputs. So you just draw the architecture. So 3 inputs, 1, 2, 3. These are your 3 inputs. You have 1 hidden layer with 2 neurons. So the 2 neurons are here. And then you have 2 outputs. As mentioned, 2 outputs. So again, you have 2 outputs here. So this is your architecture. You just put your input 1, input 2, input 3. Yep. And then you can just fully connect your neurons. As we said, it has to be fully connected. Same thing from the hidden layer to output layer, fully connected. And you can number your neurons, as I said, from 1 and so on, and then you can have unique labels for your weights and threshold. So this is your output here. Let's call it output 1, output 2, and this is input 1, input 2, and you have input 3. And number your neurons here, 1, 2, 3, and then continue labeling 4, 5, so that we have unique labels for your weights and thresholds. We know this is this threshold here is theta 4. So this one here will be theta 5. This here will be theta 6, and the last one here theta 7. We can just we can label some of the weights. This is W14 here. This is W35. We can span W46, and let's just label this one W57. We don't need to label all of them, else it will clutter the diagram. Yep. Now the question asks you to assign values for your weights. We can just say here, for example, if I get a question like this, I would say let all weights be a given value, and you can put it like we just simplify. Although in practice it would be randomly assigned. But for sake of this problem, you can say all weights, you can just choose any value you want. Let's say is equal to 0.5. Yeah, it's a bit hectic for you to assign initial weights to all of them. So you can just say all weights are 0.5 and all thresholds here, thetas, let's say it is 0.2. You can say anything you want here. Except don't put it to 0, 0, else you won't have any value and it's going to be a trivial case. Don't start at 0, 0. Yeah, although you could, you could, because anyway we get an error here, but let's take values here, 0.5 for all weights, and for all thresholds we take 0.2. Let's say. Now it means you can start by calculating capital X4 here. So capital X4 will be X1 times W1. Let's start with this one, capital X4. So it will be X1, and the value of X1 is given here, 0.5. So we take 0.5 times the weight. We are assuming all weight to be 0.5. So 0.5 times 0.5 plus X2 here. I2, the input 2 is also multiplied by the same weight, but I2 is 0.25. So 0.25 multiplied by all weight 0.5. So I'm taking 0.5 itself plus the next input is I3, it is minus 0.2. So plus minus 0.2. Multiply by 0.5 again, because we are showing all weight to be 0.5. So here you have been able to get your capital X4, and then as usual we take capital X4 minus theta 4, and we have assumed all threshold to be 0.2. So the answer you get here, you subtract 0.2 from it, and the final step is to get Y4, the output for neuron 4. You feed that in your sigmoid function. Yep, so sigmoid, I just write SIG here for sigmoid. So the value you get here, just plug in here, you get the value of Y4. So in this case, you'll find that your Y5 will be exactly equal to Y4 because all the weights and threshold have been assumed to be 0.5 and 0.2. So you will get the same value for Y5. But in normal course, you're going to also work out capital X5, capital X5 minus theta 5, and then you work out Y5. Now, once you get the value of Y4 and Y5, you should now calculate capital X6, which is Y4 times W46 plus Y5 times W56. So you're able to get your capital X6 now. Yep. So capital X6 would be equal to the value you get for Y4, this one here, multiplied by 0.5 because we are assuming always to be 0.5. Yep. And the value you get for Y5 also times 0.5, you get capital X6. From here, you're able to work out capital X6 minus theta 6. And from here, by applying sigmoid function on this, you're able to get your capital Y6. So this is known here. So similarly, you're able to work out capital X7 for this neuron. So it will be similar here. You get the value of Y4 now times this weight, which is also 0.5, if you assume always to be 0.5. And this Y5 also times 0.5 minus 0.2 for this one. So once you get this one here, you will calculate capital X7 minus theta 7. And from here, you feed this to the sigmoid function, you get Y7. Now, from Y7, what is basically Y7, student, here? Sorry, Y6, it is output 1. So this is the output. What you're writing here, sorry, as Y6, what you calculated here, is actually represented as output 1 here. So from here, you are able to work out what is the error for neuron 6 as a difference between the desired value, which is 0.8, minus the value you got here. So you're able to work out your E6. And from the E6, you can work out delta 6. Yep, delta 6 is Y6 into 1 minus Y6 times E6. So similarly, since you now know the value of Y7, and Y7 is actually represented as output 1 in your set, this is the desired value. Yep, you take this value minus what you got, you are able to work out E7. And from E7, you can work out delta 7. Now, using this delta 6 and delta 7, students, you are able to correct for W46, W56, and theta 6 using the alpha times X times delta. You are able to correct for W46, W56, and theta 6. Similarly, from delta 7 here, you are able to correct for W47, W57, and theta 7. So at this point in time, you have been able to correct for all weights and threshold connected to the output layer neurons. Now, you also need to backpropagate now the delta 6, delta 7 through these weights here to get delta 4. Let's write this, students. It's a very important step. So let me erase this part here. So next step after correcting here, you would want to find delta 4 for neuron 4. So delta 4 would be equal to Y4 into 1 minus Y4. Remember, you have all these values from the forward pass. You have the value of Y4 and 1 minus Y4. And you can work it out. E4 we don't have, but we multiply this by the backpropagated error gradient. So the delta 6 you have here will be multiplied by 0.5. And we still have delta 4.6 is the value of 0.5 in the previous situation. So you get here delta 6 multiplied by, so you have this bracket here, delta 6 multiplied by W46 plus delta 7 here multiplied by this weight, which is also 0.5, but it is W47, and delta 7 multiplied by W47. Okay, so at this point in time, I know delta 4, so I can correct for this weight, and this weight, and this threshold. Same equation, except you have to use delta 4 now, and the respective inputs. Learning rate, you can assume it to be, if you want, 0.1 or 0.2. And you can just take a value, a suitable value here, 0.2, let's say. So you have worked out delta 4, you're able to correct W14, W24, and W34, and theta 4. Similarly, you can work out delta 5 as Y5 into 1 minus Y5 multiplied by E5. We don't have E5, so we backpropagate here delta 6 through W56 plus delta 7 through W57. You are able to get delta 5. From delta 5, you can correct for W15, W25, and W35, and theta 5, and that completes your iteration. Okay, students, so this one, I won't say it's a short problem, but it's very systematic. This one, if you're given a problem like this, it will easily take like 15 minutes to do that. Yeah, it will take some time to do that. Bearing that in mind, for the test, of course, you'll be given enough time to solve the problems. You don't expect to get too many calculations as well, but we are testing your ability to apply the backpropagation. So most likely a question of this complexity would not be one you would get for the test, yeah, because you have 1 hour 15 minutes, so I would say maybe half an hour only for my part, where you have 2 questions. You don't expect to get a big question like this, yeah. But as a practice here, if you're able to do that, you should be able to easily do the respective question for the test. But this is I would say a question more for exams where you have 30 minutes to do a question like this. Yep. So the complexity would not be so much in terms of the calculations you have to do. Because in this question, I'm saying you have to complete 1 iteration. So I'm expecting you to get all the weights and the threshold, but in 15 minutes, you're not able to do that and another part of the question. Yep. So it will be of less complexity if you get the question of that. Okay, students, so just to recap, we've done 1 question, decision through learning. I would ask you to do a question like this now, which we have not attempted. We have gone in detail of this one in terms of principle point of view, but now try to put figures to these different equations and see if you're able to do 1 iteration. Next time we meet now will be on Saturday, same time. So we have 1 session on Saturday, 8 from 9. So then we can look at some further questions, and then we'll be taking further doubts you may have on what we've covered so far. Next Monday, I'll be covering the remaining topics, which is on logical programming and few other topics, which I will cover with you. And the subsequent, so we're not talking this Saturday, but the next Saturday, we can plan to have a session on campus, but it depends, of course, on your availability. And if you're doing other tests, it may not be feasible, but I prefer we do like this. If you're able to have a session on campus, I'm able to help you better. Okay, students, I've taken attendance already. Is there anything you want to ask me before we end? So it's now on your side now, students. You have a tutorial sheet. I've explained the principles to you. You need to get your hands dirty, like we say. Do give yourself enough time to practice the question so I can help you from the doubts you're getting. Okay, I've already taken your attendance. So that's done. That's fine. Any question from you? Else we can close the session. We've gone a bit over time. Yep. But that's fine. We've been able to...
For this, hello sir, for this Saturday, the session will be online, 8 to 9?
Yes, I'm planning it to be online. Unless if you can do it on campus, I'm happy to do that. But do you have any other tutorial on campus on that day? Because I understand you have 2 other modules you're doing this semester. So you have the tutorial on the same Saturday. So what's the status in terms of the other tutorial sessions you're having? Is it on campus or online itself?
Don't think we have the confirmation yet. They will tell us during the week, most likely.
Yeah, because if it is online, I can't expect you to be on campus and then do it online. So what I suggest this Saturday here, we can still do it online as we've been doing, but I want to have 1 session with you where we're able to wrap things up, like for 2 hours. So the following Saturday, not this Saturday, the following Saturday, we can try to enforce that we're going to have that on campus. Then I'm able to better help you. Yep. But again, it depends what other people are doing. Yep. I can't sort of dictate everything. If you have other sessions which are planned to be online, then it would have to be online itself. Okay. So let's just postpone that till for the time being. This Saturday, I think maybe you can update me, students, if ever you have any session occurring on campus this Saturday. I'm very happy to do the session on campus this Saturday itself, but it depends on what others are doing. So do keep in touch with me, the class rep in the class, if you have any information that if ever there's any session on campus, we can plan accordingly to have at least 1 hour. Yeah, let me know. Okay, students, thank you.
Thank you.
Thank you.